Okay, so as I said, today we will follow up from what we learned from last week, right? We start to talk about parallel programming. The good thing about parallel programming that we learn is we can make your program a lot faster. But you want to be careful, right? You want to be careful with how you design your program. Today we will discuss about different parallel programming models. Today will be more theoretical side of things. Last week it's more like, okay, we have Rust, this is how you can use it. So combining this with the theoretical side of things, hopefully you can have a better picture on how each of the concepts that we learned today apply to Rust and beyond Rust. There'll be an in-class exercise, which I actually pose it as like an outside of class exercise now. Because I then realized that not everyone know how p-threads work, so I will need to explain that to all of you. And my plan is to do it next week. Basically, this is like a classical parallel programming that C give it to you, but it's super old, to be honest. It's good, but it is quite old. So I will need to explain how that works, but basically, I'm going to explain during an in-class exercise time that this is basically what I want you to do, and it has to do with rest condition, which you learn what is that. All right. So one thing that I did not have time to do, well, we do have time, but I finished early, sorry. We are supposed to talk about the parallel merge sort, right? So let's first go over merge sort, because my assumption is not all of you took data structure and algorithm class. So how many people know what merge sort is? I'm sure a bunch of you know about merge sort. Okay, awesome. So for those of you who know merge sort, help me guide the rest of you who haven't taken data structure or algorithm. Basically, help guide your underclassmen. What is merge sort? What's the difference between merge sort and quick sort? And it's okay to say things that you're not sure. Just be don't be shy. If it's going toward the correct direction, I'm gonna basically guide it toward the correct direction. Don't worry, I can do it on the fly. So that's one of them. Basically, quick sort, right? You pick a pivot, then you break things into two chunks based on what's lower and what's higher than that pivot. Merge sort, one of the key differences, we don't pick a pivot. We start by breaking the array in half, and then breaking the array in half again, breaking the array in half again. The reason why they are named merge sort is you start sorting when. So basically, there are two processes that you have to do, right? Breaking things in half and merging things back. So when do you start to do the sorting? Yes, basically each time you split, you keep splitting, right? And when you combine, when you ended up with one element, that's when you start to do the sort. The reason behind that is when you start doing the sort, every time you merge, you compare who goes first, who goes last, right? And why is that good? Why is that good? So let's say this is our array. While I'm waiting for your answer, I'm going to start drawing so that for those of you who haven't learned merge sort, you see what is that. Basically, what is merge sort? I will start with an array with, I guess, 8 things so that we can break this into multiple chunks. Okay, that's not definitely not 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 things that are totally not balanced. Anyone want to give me a number? 8 numbers. And hopefully these are not sorted. 8 to 1. Okay. Let's at least make it a little bit more, like more or less a little bit not as sort the other way around. So let's start with 8, end with 1. And I'm gonna know 7, 6, 5. No. That box is supposed to be a number 1. 5, 4, 3, and 2. Okay, let's start with that. We have 8 at the front, 1 at the back, and somehow we want 1, 2, 3, 4, 5, 6, 7, 8. Right? So what merge sort would do is it would first break things in half, as everyone here who knows merge sort tell me. So how do you get that? You break this in half, 7, 4. The other half would be 2, 6, 5, 1. Right? And the reason why we call it merge sort is we haven't sorted yet. We keep splitting into 8 and 3. And then 7 and 4, 2 and 6, 5 and 1. And then you are going to get 8, right? 3, 7, 4, 2, 6, 5. And now I realize I have no area left to draw. So I'm going to use a different color, blue, to represent the merging part. So when you merge, you start doing the sort. If you want to merge 8 and 3, what merge sort would do is we would pick the front of the two collection. This is a collection that consists of number 8. This is a collection that consists of number 3. The front of the first collection is 8. The front of the second collection is 3. Which one has lower value, 8 or 3? 3, right? So basically you start building, basically merging the two collection together. You compare the front, you see 8 and 3. Okay, 3 is lower, so you first put 3 in, followed by put 8 in. The same thing goes for these array, right? 4 will be put in here, 7 will be put in here. This is already sorted, so 2 and 6 will be put here, and then 1 and 5 will be put here. All right, so what do I do next when I go up? Basically, I'm going to draw an arrow here. The blue mean I'm going up, merging. Red mean I'm going down, breaking things. Okay, so what do we do next when I merge? I'm going to merge 3, 8, and 4, 7, right? I will merge 3, 8, and 4, 7 together. And then the other side, I'm going to merge 2, 6, and 1, 5 together. How do I merge? I'm going to look into 3 and 8, 4 and 7. I look at the front. I just look at the front, which is 3 and 4. Which one is lower? Between 3 and 4, which one has lower value? 3 or 4? 3, right? So I'm going to compare these two numbers and I'll say, okay, 3 is lower. I put 3 in. The next number is 8. So I'm going to compare 8 and 4, right? I'm going to compare 8 and 4. Which one is lower? Between 8 and 4, 4, right? Then I'm going to compare 8, which is the same elements. 4 is already going up, so I will compare 8 and 7. The lower number is 7, right? And then the rest of the number is 8. Over here, you do the same thing. You compare first 2 and 5. You put 2 in first because 2 is the lower one. You move the index to now 6 and 5. 5 is now lower, so you put 5. My bad. I somehow look at the red thing instead of the blue thing. So basically you have 2, 6 and 1, 5. 2, 6 and 1, 5. You compare 2 and 1, right? 2 and 1. You first put in 1. This index now move to 5. You compare 2 and 5, you put in 2. You compare 6 and 5, you put in 5 and 6. Any questions so far about merge sort? Any questions so far? All right, so we're going to merge the last collection, which is 3, 4, 7, 8 with 1, 2, 5, 6. One thing that you will realize here, every time we merge, everything inside the collection is sorted. Right, the algorithm for ordering of the sort. Is that a question? Sorry, I was trying to understand, is that a question or is that an answer? Because it ends with the question mark. Oh, what's the order of the index? Basically, you have a pointer that points to the head of the collection, right? And because we assume that both collection of things, like right now the two array are already sorted inside the array, so we can just have a pointer pointing at the front, because the front is the lowest, right? And then what merge sort would do is could compare between the two elements. The lower one would be put in the next collection, will be merged. When you merge, you put the lower one first. The index moves to the next item, depending on which one is the lowest. So I think you see this example when I merge the two array here, array A and array B together into this result, right? So when we want to merge 3, 4, 5, 6, 7, so we have 8 elements. You first point to the front, right? Because the front is the lowest of each element. Right? What's the order of index we choose for sorting? Basically, it's always point to the front. It's always point to the lowest element. No, sorry, my cat was trying to like walk on my keyboard. All right. Yeah. Okay, so between 3 and 1, which one is lower? The index now point to 3 and 1. 1, right? So we put 1 in. It moved from 1 to 2. Between 3 and 2, 2 is lower, so 2 puts here. Move to 5. Between 3 and 5, 3 is lower, so now you put 3 in there and move to 4. 4 in. 4 move to 7. Between 4 and 5, 5 is lower. 5 move to 6, 6 is lower. You're done with this. Yay! So you know that the rest are 7 and 8. Right? And now you have the sorted array. So this is merge sort. Any question about the merge sort before we go to the parallel version of merge sort in Rust? Yes, you move the pointer of the collection that holds the smaller value one by one by one when you perform that comparison. All right, sorry, my cat is like fixated on the keyboard, so I need to hold her. Any other questions before I turn this into like a cat channel? Okay, so if there's no more question, let's do a parallel merge sort. And here's the code. I'm gonna go through them slowly. This is the main function that we want to do merge sort. How do we do that? We first use a parallel iterator, right? XS is our array that we want to sort. XS is the array that we want to sort. Why? Okay, my first question, Rust-based question. Why do you put ampersand here? Why do we need to put ampersand here in the type of XS? It's actually not about mutability. We just want the ownership. Ampersand is about ownership. MUT is about mutability. If you don't say MUT, it means it's read only. This M sort function would just read XS. it will just read as. I'm gonna take the ownership by borrowing, right? By borrowing, say, hey, whoever give this value, hopefully I can borrow it. Then you clone x, right? Because it's not mutable, I need to make a copy. I need to make a copy so that I can store my results. Then I perform a map, right? So let's break down this green thing. But before we break down the green thing, which is like the parallel version of these, we will move to the red and blue thing. Because basically the red and blue things are what we covered in the last slide. These are the merge sort, right? These are merge sort thing. This is the merging part, right? It looks at two collections, the left and the right side, XS and YS. XS is the left, YS is the right side of our array. And essentially, this part is look at the first element, right? When both of them have something, you look at the first element. If XS is smaller, which is the true result here, you push XS into CS. And then you get rid of the first element of XS. What's par-iter doing? Basically, par-iter, yes. It's not supposed to be lowercase. This is supposed to be par underscore iter. Is everyone here know what is an iterator? Par-iter. Basically, par-iter is I'm gonna iterate, but I'm gonna do this in parallel. It allows you to kind of like access a bunch of elements and iterating over all the elements, but this is done in parallel. Is one of the nice thing in Rust that's already built in that you can call. It would give you all the elements, but this process is done in parallel, so it should be quicker. Can I ask for a brief summary? Is it brief? Do you mean brief summary of the parallel iterator or brief summary of the iterator? Okay, sure. So over here you have an array, right? Basically, anytime you have a collection, list, array, set, map, right? It means that you can go through all the elements, right? Dot map in Rust is the same as Scala. It performs the mapping when you define a function. It applies that function to the element. So it's the same thing. One thing about iterator is you can actually go through all the elements. These collection, if you can go through the elements inside the collection, the process of going through each element and give and return each individual items is called iterating. You iterating through all the elements. The object that perform that iteration is called iterator. Basically, is an object that you can call. And iterator, basically, if you have iterator, or I'll just write ITR because I'm lazy, I don't want to write the full word. You can do .next in Java, it would give the next thing. And you can do .next, which means that it's going to check your set. And if you go through all the elements, .next will return 0. If it still has something left to go through, it will give you the next item. Does it answer your question? Basically, for a brief summary of the iterator. For array, what it would do is go through this, right? And would first return A, followed by B, followed by C, followed by D, followed by E, and then afterward next will be false because you are done going through this collection. So does it answer? Also, any more questions about iterator? Because I mean, I totally don't mind making sure everyone here is on the same page. Yes, no. Okay, I would take the long pause as this is good enough for the explanation. I'm confused. You confused on reduce. You mean this part? Okay, so what does reduce do? What does reduce do? By definition, reduce would perform an operation on two things. Basically, okay, not two things, but it's a pairwise operation. So let's say you have, do you mind if I create a new slide to talk about reduce so that I can come back here without like making this like a fully messy page? So let me quickly do that. Otherwise, this would get really messy. Let me keep this. I need a new slide here. All right, so I will just do iterator and reduce recap. Iterator, I will just draw it because I already explained it. So basically, if anyone look at the slides afterward, they still see the annotation. So you can go next, 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 and next. So this is iterator. Reduce will do this. Reduce will take a collection, and let's say your reduce want to add things together. Let's say your reduce want to do the add. What reduce would do is it would pick each element, it would pick a pair of this. If it's an add operation on an add function, it would add them together. Pick each of these two, add them together. This is the only one thing left, so you don't add it yet. You would then pick the next two pair, add them together. This is not done yet, right? You add them toward the end. This is the result of my reduce. So does it answer your question? Basically, you take the collection, you do pairwise operation on each pair. After you've done the first pass, you do again pairwise operation on each pair. Again and again and again and again. So my quick question, if I need to do a merge sort, what is a pairwise operation that I need to do? So if I need to do a merge sort, right? Yes, you need to merge. Basically, now you break things down into each individual element, right? Like this. The next step is you need to do a merge by comparing left and right items. So this is the merge. You merge the two array together, right? You ended up with a bigger array. You do the merge again into a then bigger array. And then you do this on and on until you're done with the whole thing. So is it now a little bit more clear on what reduce is doing on this code? Yes. So basically this whole thing, what it does is you would first make a copy of XS, right? Is the array. So the question is, what does Iterator doing is go to do that operation on each item of the list at the same time. That's not what Iterator is. Iterator just return a bunch of things. The doing the operation is the map and the reduce. Is the map and the reduce. Map over here, map is just creating the result list so that you can write the result into. The reduce part is when you apply the merge. when you apply the merge. Right? This is when you actually apply the merge. So does it answer your question about the parallel iterator part? Okay, awesome. So now you know at least the high level. The bottom part, the M sort part, is the big function that we need to call. It would first get everything. Sorry. Yeah, again. The dust is coming back, guys. So wear your mask. If possible, wear down to N95 if you have them. The air quality is getting worse again. Anyway, so these long line of code, the green part, you want to put results in the vector, and then you want to do the reduce on the merge function. The merge function is essentially this thing, merge function. What does merge do? There are two things that a merge do. First, well, this is preparation, empty list. Oh, it's a vector actually. A vector is kind of like an array, but you can add things on it. So you create a new vector. Then you look at left and right side of your item. Then, depending on which one is smaller, the left side or the right side, you push the smaller one to my newly created list. And you do this again and again and again and again. Like, why do you do it again and again? There's a while loop here. While we are not done, during this merge, we'll push things in. When either the left side and the right side is gone, like basically you go through all the elements, you would then append the rest of it. So you append. So this is basically when XS and YS, there's nothing here. So you basically put XS into the end of CS. Right? Basically you just make sure you have a sorted array. Then you return CS. So basically this is when you return. Right? So these allow you to do what in parallel? So what is now being done in parallel? It's doing the dividing and merging in parallel, right? What is not in parallel? What is not done in parallel? Let me know if this is still. Let me know if this is still confusing so I can explain it, please. Okay. Yeah. So the question is if you're still confused with M sort, but you okay? Who is still confused with the merge? Because let's break it down into the merge part and the M sort part. And yes, that's a great answer. Everything in the merge part is not in parallel. Those are sequentially done, right? When you merge, the comparison is not parallel. So that is the bottom. That potentially becomes the bottleneck. What is these doing? So another question is, what is this part? This part is essentially, I'm gonna leave out the first item of XS. XS is now, I cut the first item. I remove the first item. the rest stays in there. Why can we do this? Because we just declare mute XS on the second line right here, right? Okay, so I think at least any more question about the merge part? A quick yes or no would be good. So if you still have questions, okay, awesome. So then let's talk about MSort part. So now that we know how to merge, what is the rest of my task? I need to break things, and I need to basically call the merge, right? I would need to call the merge. Yes. Okay, let me make another copy of this same slides again, so I have a fresh copy that I can talk about the merge part. All right, so this is a fresh copy of the same code. I still retain this old copy of the code, so you can take a look at the slide with two different pages. Now let's talk about the M sort. What do we have initially? You have the unsorted array, right? So I'm gonna draw the unsorted array with the red text. This is unsorted. What is the first thing we do? We iterate over everything so that we can clone this. So we will get this clone copy of the unsorted array. Then you start doing the merge sort by doing the reduce on left side and the right side, right? That's our function. This parallel iterator, instead of giving this one giant list, the green thing that you clone actually is each individual items of your unsorted array. Right? You have a bunch of items. So this is what happens when you do parallel iteration and clone. This is what you get. Then you perform the reduce operation. What does reduce do? Right? Reduce do a pairwise operation. What is my operation? My operation is the merge. Right? My operation is I want to merge based on how I define it. So you apply this on the first and the second items. So you get two elements. You apply the merge on the third and the fourth item. You get two elements. You get two more elements here. You get two more elements right here. Are you with me so far? So this is the reduce part. The map here is basically, if I have an item, I create a vector of item so that this is the type vector of E instead of elements. That does nothing much. Basically, I just need to make sure everything is on the same type. So instead of one single integer, I just have a vector of integer. Then I do the reduce. And now the next pass, because, oh, you mean you mean this thing? So that thing means that I would do this in parallel. The symbol, the vertical sign, the two symbols next to each other means that I'm gonna declare, hey, this can be done in parallel. So please do this in parallel. Okay, that's another great question. Oh, this is okay. Sorry, one by one. What is E? This E, it means that it's a anonymous function. I'm declaring a function that take E as an input, and I'm going to create a vector. Oops, sorry, a vector that consists of E. So that's what the vertical sign with something inside mean? A vertical sign with something inside means that that's a function and it takes those things as your input. What comes after that vertical sign is the function body. So does it answer your question about what is the absolute D? Okay, then why does the vector doesn't have anything inside, right? So what is this? That's an empty vector. Basically, it's an empty collection. Why do we need it? When you perform a merge, you need to write the result somewhere, right? This is what you return. You return this. So you basically need to put those things into my vector. Oh, how does reduce know that there will be LS and RS? Uh, this is pattern matching. Basically, when you do a merge, right? Not when you do a merge, when you perform a reduce, what happened is I'm gonna pick two things. I'm gonna pick two things. That two things happen to be these and this. It's a vector. So there'll be a left side and the right side. So there's always going to be the two items that you perform the reduce on. The LS and RS, it's just me declaring that, hey, this is pattern matching. LS would map to the left side of that operation. RS would be mapped to the right side of that operation. Then you perform the merge. So the next step would be you merge these two together into four things. Right? This become LS, this become RS. Same thing goes here. This become LS, this become RS. You get this side. And then this become LS, this become RS. You merge. So you get the sorted array at the bottom, which I ran out of room. So any questions? All right, so hopefully this clears things up a little bit. A lot. Hopefully, basically, what I'm hoping for is this is now more clear than 5 minutes ago. All right. So if there's any more questions, feel free to type it in. I'm gonna take a look. I'm gonna keep looking at the chat, but I'm gonna move on to the next the topic that we would like to talk about today. So today, so we call merge inside reduce. Yes. Basically, the question is, so we call merge inside the reduce, right? So yes, the answer is yes. When you perform a reduce, basically you pick two items, you run a function that you want to run on the two items. In here, the function is a function called merge. The merge would basically combine two collection into a vector. Do we need a vertical line between LS and RS like that? I might have made a bug. Let me double check. Give me about 1 minute. Let me double check with my the source code in my notepad. No, I don't think so. You don't need the input. Okay, you don't need the vertical line because those are not functions. The function is merge. Merge is already a function, and you put LS and RS as an input. You need to kind of break it down into the left and the right side. LS and RS are not defined before. You do pattern matching to define LS and RS based on the elements that you see on the left and the right side of your items. Okay, so let's talk traditional multi-threading, right? When you buy a computer these days, even on a mobile phone, what will you get is multiple processor, right? Multiple processor. These days you're looking for eight. So each thread is assigned to run each thread that you created. If it's parallel iterator, if it's parallel function, these subtasks are supposed to run in parallel. They'll be mapped to one of the CPU that you got on your computer. And if the number of threads or number of tasks that you have to run is way more than the CPU, and that's always true, right? As I said again and again and again, most of you, including myself, always has 5, 10 different Chrome tabs. Each of those tabs are one task, right? They will be taking turn running on a CPU. So the OS and the hardware are the one that has to perform that mapping. And if you took the OS class, you might have had fun or not fun with the lab that scheduling task to the CPU or the processor. There's also hardware multi-threading, where one CPU can also have multiple hardware threads. We will cover these toward the end of this class, but before we begin about how this actually works when you look at a computer and you have a parallel program, let's talk about how to create a parallel program. How would you think about the parallel program beyond what we learned from Rust? So a lot of things that we do in Rust is being made easier, right? You can do just double vertical line and say, hey, this can be done in parallel. You can do ampersand to give the ownership and things like that. When you need to create parallel program in a different language, there are certain, I guess, guidelines, right, that you're supposed to follow if you want to avoid bugs and things that might make your code wrong. So to create a parallel program, generally speaking, these are the steps. First, you have a big problem. You need to break big problems into smaller subproblems. You decompose the problem. Then, when you have the subproblems, you assign the worker to work on each subproblem or task, right? Most of the parallel program libraries, APIs, all the paradigms that you see will follow or typically follow these steps. You first breaking things into multiple subproblems. Each worker will work on each of the subproblems, right? The thread pool that we have earlier from last week also is looking at these worker threads. It picks the task and it runs the task, right? And then when you're done, you combine all the results of the subtask so that you have the results of your big problem. The last step is called orchestration and synchronization. There are many, many, many things across all the three steps that can lead to poor performance. So we will talk about what you have to be careful and what you have to think about when you design a parallel program. The reason why I go through these content while it's more theoretical, I want to make sure you're careful about writing a parallel program. It's not too hard to make a parallel program that run. It's harder to make a parallel program that run fast, right? So what we are going to learn today will be on how to have a parallel program that runs fast. Sorry, again, he really want to walk on the keyboard. The first step is called decomposition. The key issue on decomposition as a programmer is what can be done in parallel. So this is what we cover in the last lecture where we talk about work and depth and parallelism, right? This is exactly what parallelism means. You work divided by depth. If the work divided by depth is high, it means that you can do a lot of things in parallel. What about dependency? even when you can do a lot of things in parallel, sometimes you have to wait for certain things, right? You have to wait for certain things. For example, right, if you have a parallel program where task 1 and task 2 generate results for task 3, right? These relationship is the dependency. It means that task 3 depends on task 1's and task 2's data. Remember Amdahl's law. You want to make sure you can parallelize things as much as possible. The next step is assignments. Actually, any question about the decomposition? This is essentially work divided by depth. This has a lot to do with the algorithm. This has a lot to do with how to design your algorithm to solve the problems. You want to make sure these are as parallel as possible. This is actually in modern day computing, this actually matter a lot for performance, right? So one thing that I really need to make sure you consider are things that, let's say you run a startup company, right? Let me put it this way. How many companies that you can use to order food from? Can someone help me listing them out? There's Grab, right? There's Lineman, there's Food Panda. I don't even know what else. There's quite a ton of those. Eventually, right, they would not just compete on promotion and things. At some point, they will compete on how fast they are, how accurate they are, and whether you can handle a lot of parallel. Basically, server can handle a lot of parallel requests where the user, hey, I need to do this, I need to do that. The decomposition part, basically when you design an algorithm, make sure you can make it fast because that can itch out when you have to compete against your competitor. The second part is assignments, right? Assignments is basically now that you have a lot of sub-problems you map to a threat. The design goal is to balance the load and minimize communication, right? These assignments can be done statically or dynamically, and this can be assisted by language and runtime. That's why we use Rust in this class, because when you program in Rust, this is done like almost automatically by the runtime behind Rust. For the assignment part, when I talk about load balancing, right? Let's say you have task 1, task 2, task 3, and task 4, and you need to finish all of these 4 before task 5. Task 1 take 1 second, task 2 take 1 second, task 3 take 1 second, and task 4 take 1 hour, task 5 take 1 second. How long do I have to wait until I finish this program? Assuming that task 1, 2, 3, and 4 can be done in parallel. Assuming that task 1, 2, 3, and 4 can be done in parallel. 1 hour and 1 second. Yes. And be careful about the letter you type in. It's okay. I know this next to each other. For letter X and letter C. So basically, this means that I'm gonna finish task 1, 2, 3, right? And T4 all together. It just happened that T4 takes a long time. There'll be a time where everyone has to wait before you finish T5. So this is basically 1 hour and 1 second. I need to make sure I don't type it wrong. So that would take a long time. And the problem here is thread 4. Somehow that particular task takes so much time. In reality, these can actually reduce the performance of your parallel program in a cloud environment. Like, do you actually submit a job to run in Amazon? And then you're like, this is supposed to be fast, and somehow it's slow. This can happen. One of the threads is slow. If one of the threads is slow, there are multiple things you can do. One of the things is, well, make the task smaller. Break task 4 into, say, task 5, task 6, and task 7 if you can, right? Where each one of them take 20 minutes. Then now your program would run and finish in 20 minutes. 1 second. Another thing that can happen, it might not be the fault of the program. It might be the fault of the machine. This actually happened in the cluster at TGGS, in the mechanical engineering program over here. They have a cluster that consists of 3 generations of machine. The oldest one, the not too old one, but still old, and a new one. And somehow, the company that actually charged us, right, the money to manage the cluster, I don't know what goes into their brain. But what they do is they bundle all the machines together. So what happened is the professor in the mechanical engineering submit a parallel program to run some simulation models to basically look at things like what will happen if the car crash, right? Will it hurt the human inside the car and things like that? And it turns out to be really slow. Anyone want to take a guess why is it really slow? So you have 3 set of computer, really old one, not too old, and a new one. This is fast, this is okay, and this is slow. What might happen if I run a parallel program in a cluster that the admin somehow merge all these 3 set of machines together? Yes, some of the tasks get submit here. T1 and let's say T4, you submit T2, T5, T3, and T6. Looks okay. Equally equally distribute all the jobs to all the machine. The problem is T1 and T4 will take forever because they are slow, right? So if you are working in an area that involved with cluster computing, how to maintain a server and things like that. These will and should not ever happen. I'm kind of like furious about it right now that I know about it. Like, why would someone who graduated from an engineering program in Thailand, who claim that they are quote unquote expert in computer system, which to be honest, there's not that many experts in Thailand in this area because I'm in the area and I know that there's none. No, not many people in this area in the country claim quote unquote they're expert and do this because it's dumb. There's no better word for it. It's this is bad, right? Basically this is one example where you try your best at parallelizing your program and somehow it's still slow and you somehow detect that some of the threads get mapped to a slow machine. This problem is called the tail latency. It's a really, really common problem in a cloud, like a large cluster of machine like Amazon, right? Where some of the tasks can suddenly get mapped to a slow machine. What they usually do here is they'll remap it back, right? Remap it back to the fast machine, and hopefully your program, they detect it early enough so you don't feel like there's something slow on it, right? Any questions about this? Because I think I went sidetrack a little bit toward the OS and the system side, this distributed system, basically. When you have parallel program, it's closely tied with the concept in distributed system. And this is where you can lose performance as well. All right, so let's talk about the last step. The last step is now back on your plate. This is this matter for how you write the program. Orchestration. You need to organize the results, right? Once you have all the subtasks, right? So you have task one, task two, task three, task four. You have input, you have output. This one has input, you have output. You can have input, output. Somehow you need to actually merge all the outputs into one single output, right? For example, for our merge sort, when you do merge sort, right, the reduce operation has to merge, has to actually combine the results together. The combination is done in the definition of the merge function. One thing that one of you said, the problem with the merge function is what? It's done sequentially, right? Any one of you realize that the merge function is done sequentially? There's nothing parallel in that function. So that becomes the bottleneck. That merging, where you compare the two elements and you compare that one by one by one, that can become the bottleneck because you need to synchronize, right? You need to synchronize, you need to wait, you need to preserve all the data dependency over here. When you merge the two array, you would need to make sure you're done for the first item, so the second item, and blah, blah, blah. Sometimes it might even involve scheduling more tasks, right? So the issue is you want to reduce these costs, right? You want to reduce this cost. And it depends on your algorithm. Depends on your algorithm. We'll talk a little bit about shared memory and synchronization after the break. Before we go to the break, the last thing we need to tell you is, well, when you have parallel program, when you have all the tasks, everything is done nicely. When you run it, this get mapped to hardware. This is a combination of the operating system, compiler, and the hardware working together to actually give you a fast program. Right. So now that you have a parallel program, it's basically my job as a hardware designer, as a system designer, to actually deliver an actual like fast program. So some of the trade-offs are basically how can you make better use of the memory? How to reduce amount of communication between each of the tasks when you have shared data. Rust, one tidbit is Rust is really good at giving all those hints. So as a hardware architect, right, make our life much easier. Uh, like if you want to maximize independent threads, you can get a lot of parallelisms. So that is something you can do as well. This is actually what the GPU, which is one of the really massively parallel machine, can do. So now that we finished the how do we actually translate your parallel algorithm into parallel program in Rust into essentially the process of mapping this to hardware. Any question before we take a quick break? Let me ask you one quick thing. How many of you tried running things in the cloud before, like using AWS or some services? Okay, good. So uh, things that we covered today from kind of like after the merge sort until now and going forward will kind of like also involve discussion about things, programs that you run in the cloud, especially once you have parallel program. Uh, so hopefully this might interest those of you who tried running things in the cloud before and interest those of you who never tried running things in the cloud before. I will talk about some of the potential problems when you have a bunch of parallel program mapped to a lot of servers on the other end, right? So we'll talk about this during the second section of this class. It's called the programming model. Let's do a 15 minutes break because we've been kind of covering quite a lot of material. During the 15 minutes break, if you have question, again, as usual, please feel free to type it in. Uh, we'll meet back at 10:35. Is that okay for everyone? All right, awesome. So we'll do a break and let's meet again at 10:35. All right, so I'll be back. Hey, and yeah, during the break, feel free to just chat. Uh, you make me kind of reminds me of like undergraduate days where I'm still playing lots of games. Okay, so let's resume our class. Let me actually check if my cat is eating something weird. Okay, so let's talk about the programming model. So, what does it mean when you mention programming model in the context of parallel programming? Essentially, when you talk about programming model in the context of programming, parallel programming, is essentially we're talking about three kinds of techniques that you can use to manage data. That's what the main focus is at, because essentially the data is what you cares about and what eventually these becomes your results, right, for the function or for the program that you're running. So there are three programming models. The first model is called shared address space. The second model is called message passing, and the last model is called data parallel program. The last one actually these days being popularized in certain really specific aspect. One of them is the GPU. Uh, and actually not just the GPU, but things like TensorFlow and all a bunch of machine learning model use data parallel model as a way to parallelize things. So let's cover the first topic of the three different programming model. The first model is called the shared address space. So essentially, when you look at the shared address space, this is what it is. Sometimes we call this a shared memory model. It actually governs how do we deal with sharing, right? When you have to share the data, how do you communicate between each threads? Why do we have to care? When you have multiple tasks, some tasks share the data, so you need to synchronize on who gets to write and who gets to read that data. This is done in most programs. This is done through locks or mutex. Locks basically is also shared. So can anyone define me what does lock mean in human language? Locking. Exactly. You restrict access to something, right? And this is exactly the same thing as locks in program. When you lock the data, it means that I'm going to restrict access to that piece of data all the time to avoid these thing called rest condition. So whenever we refer to rest condition, it means that let's say you have a shared data and the shared data is shared among thread 1 and thread 2. Both of them want to read and write to that data. So let's just talk about one scenario of the weird or bad thing that can happen. Let's say T1 gets hold of the data and you didn't lock it. Basically, anyone can still read or write to it. Then T1 modify the data, but while T1 is modifying this data, T2 comes in, yay, and try to read from it. So the question here is what will happen to the data that T2 is reading because it's in the middle of writing, right? Will it be the old version of the data or is that a new version of the data? Who knows, right? this is exactly what race condition is. So I'm going to give you a real life example. Let's say you have a bank account and toward the end of the month, you're almost using all the salary or like your monthly expense. So you only have 1,000 baht left on the account, right? And by accident, you drop your ATM without knowing, right? So someone took your ATM at the same time because you're hungry. You go and hey, you have the book bank, right? So you can go use the book bank at the bank, right, to withdraw 1,000 baht. But at the same time, the thief took your ATM, took it to try to withdraw 1,000 baht from your ATM, and somehow let's assume that he knows your passcode, or he or she knows your passcode, so he or she can actually withdraw 1,000 baht. What will happen if this is going on? Can someone tell me what will happen? Both can. So one thing that can happen, you report to the bank saying, "Hey, let me freeze up this account. I lost my ATM card." Both have no access. Another thing that can happen, both of them have a valid credential, right? Because the thief knows your passcode somehow. So, uh, so if the bank doesn't write a software that has locks, that can happen. Both of them will get 1,000 baht. So duping money, right? What's supposed to happen from the bank point of view? Inflation, yes. Uh, good. You now type in what you learned in macroeconomy. So inflation happens because everyone has money, and those money is not a real thing. It's just a way to transfer goods. Okay, let's come back to our computer science topic. I think we are in the middle of the ocean right now with the discussion. So what's supposed to happen if you're at the bank? One thing that definitely should not happen is cat eating tissue paper. So from the bank point of view, how can you basically from the bank point of view, the bank will make sure they don't lose money, right? If they give you 1,000 baht and if they give the thief at the ATM 1,000 baht, the bank lose money. Right? Somehow 1,000 baht appear magically out of nowhere. It's a bug in the software. From the bank point of view, what's supposed to happen is they need to put a lock on your account at the instant someone tried to have a transaction that say, I need 1,000 baht. Right? So basically, this is similar to have thread 1 and thread 2, right? Both of them want to withdraw. They race to this shared data. Thread 1 got there first. Your account. You say, I'm withdrawing. Right? To withdraw, you put a lock on it. So you can actually withdraw. So this is the withdrawing part. Thread 2 got here to your account, see the lock. Thread 2 basically say, hey, I can't get in. You withdraw 1,000 baht. So right now your account at this point has 1,000 baht, right? At this point, you're done. Your account has 0, right? You are now literally broke because you just withdraw 1,000 baht. And then you're done. You have 1,000 baht in your pocket. The thief now try to access the data again. At this point, you unlock. So thread 2, the thief comes in, try to withdraw the money. What is the money from the bank point of view on this account after you unlock the data? Is it 1,000 or is it 0? 0, yes. So you will not be able to withdraw the money. All right. Quick thing, if this happened, what you're supposed to do in the beginning, put that lock on your account. Basically, make sure no one can access it and resolve what's going on. But this problem, hopefully this example show you what potentially can become something dangerous from the bank point of view. It's a program, right? It's a program that manages everyone's account. This is a piece of software. It's connected through ATMs and your bank, right? Anyone ever think about if this situation happen, how do they deal with like the time does it take for the ATM to actually see is there a lock or not? Because they're at the two different computer, right? ATM is its own computer. Your bank server is another different computer. So what does it mean? It literally it depends on the implementation, right? But one thing that this can mean is your data, the data on how much money do you have on the bank is locally located on a bank server. Both, it might be a bug occurrence. Yeah, so that can, I'm not sure we heard some random news that I've seen like once every couple of years where some random ATM becomes buggy and they just withdraw money without actually deducting the total from your account. I think I've seen once or twice in my life. So those can be bugs that happen on each of these machines, right? But what's supposed to happen is for these type of data. Oh, you have bugs on your internet banking account. Good to know. So I'm gonna be more careful with my internet banking account. So is it like locking your account or something happen? I mean, it's okay not to tell me what's going on actually. Oh. Oh, okay. So you withdraw the money and the remaining money is still saying the same thing. So those, if you, so to put it this way, those problems, sometimes it's a bug in the sense that the money is not updated. In reality, what we call this eventual consistency. Eventual consistency means that eventually you see the most updated version of your data, right? It means that you withdraw the money, eventually you see the correct total. It means the transaction is already somewhere. It's actually getting to the server so that the server can update the total. Locking that account to withdraw is a different story because you can send just a lock request from your phone. The account will become locked to wait for your transaction. And sorry, I don't know why my cat is so active today. Sorry, like the reason why I sometimes look around because my cat is literally trying to like walk on my keyboard and everywhere on my desk. Yeah, that noise is from my cat. So eventual consistency means that eventually you see the updates. These happen a lot in things like Facebook, right? How many times that let's say you post a picture or something on Facebook or Instagram, right? And then your friends have to wait a few minutes until you can see that or see that post, see that new picture or post or new text, new things that you share. Yep. So this is because of eventual consistency. Facebook just have to make sure eventually everything will be up to date, right? Do they care about whether your friends see your post in the first minute or the first second? They don't. Within the first few minutes, that's okay, right? It's good enough. These can reduce the burden on the server. The problem that one of your friends told me privately is about the withdrawing the money and the remaining money is not updated. That's more severe because you're supposed to see that. Yeah, so that's a bug, but it is still, I think, will be backed up by this eventual consistency. So eventually you see the update. At the end of the day, from the bank point of view, right? From the bank point of view, it needs to make sure it writes the software in a sense that the rest condition don't happen. You need to make sure it's secure. It don't print money randomly. To do that, we can use what we call mutual exclusion. Mutual exclusion is to basically designed to prevent race condition. Right? Let's say you have a thread that do this task. You first load a value from an address. You add one to that address and you store the update value to that address. So there's three operations: load, increment, store. Load, increment, store. What you want is no one else should be able to load or read the data right before when you store, because you already updated that data. You already add one to it. So let's say this is 10. This time it's 11. So this is your data, right? Data that is feed by thread 1 point of view. Threads 2 point of view, they'll see the data, the same piece of data. They'll see it this way: 10, 10, you haven't stored yet, 11, right? So you see that there's these time windows where there's a discrepancy between what thread 1 see and what thread 2 see. Any questions so far? Any questions so far on, there's a small time windows that each thread see a different data, different value of the same data. So what you really need to enforce is something called, you want the atomic operation across these three things, right? After you load the value, right before you add, you're supposed to lock it. No one can read from it because I'm going to modify that data before I write to the data, right? So you can enforce what we call mutual exclusion using multiple things. The first thing is called mutex. Mutex stands for mutual exclusion. You can lock it by, in C, for example, you can say lock and unlock. This is your code. The code that actually use the shared data. The code that use the shared data. Some language also has this atomic operation support by just declaring things like atomic in the bracket, critical section. So the increment and the store will be inside the critical section, right? So from the earlier example, this is the increment and store to address. Increment basically from 10 to 11. These supposed to go inside the critical section because you are modifying the value that someone else also own. Why is this not a problem in Rust? Anyone want to take a guess why this is not exactly a problem in Rust? So atomic automatically wait for other processes. So that's a great question. This is not about Rust or anything, but when you have atomic operation, two things can happen. It's either everything inside back bracket finish or nothing happen. So it's either, so let's say this is state 1 of your data, and this line after the critical section is state 2 of your data. Your data will either be in state 1 or state 2, not in the middle. So it's either everyone see these changes or no one see the changes. So this is what atomic is defined. When you have atomic operation, you either complete the whole thing, or if you go through the middle and something happened that's interrupt, you revert back. Basically, the computer will revert back your data to the point of entry. Basically, it would act as if nothing happened. So does it clear up your question? Okay, so it doesn't necessarily mean that it's waiting for other processes. The only time atomic has to roll back is if you're running something and it just happened that other process want to read the data. So that's the only case, right? Basically there are only such a small fraction of cases. For example, over here, if you look at this, right? What's the percentage of time that thread 2 would happen to read the data right when add happened? Right when add happened. It's so small, right? So most of the time, that does not happen. So when you have atomic operation, the assumption is generally everything will go through like normal. Otherwise, if like 1% or 0.1% of the time something happened, you roll back and you try again. Then let's come back to the question about why is this not a big problem in Rust? Remember our ownership thing? How many entity can own your data at once? How many entity? One, yes. So only one thing can own the data. And if you want to modify, let's say it's mutable, you declare that your data is mutable. How many things can write at once? How many things can perform the writes? Again, one. It by default guarantee there's no rest condition because of this constraint. And by default, because that's the case, there's no case such that someone's writing to it and then someone else is reading from it. Because if you are owning a mutable variable, no one else can access it. The only time you can do parallel operation on the data is the data has to be read sharing. Read sharing means that everyone can look at the data, but you guarantee no one is going to modify that data. So that's why this is not a big problem in Rust. The bigger problem in Rust is you need to reduce the number of mutable variable that you use, right? Shrink the time windows that you need to declare, hey, someone is writing to this part. Sometimes this also provide hardware support. For example, atomic operation is supported in the GPU. The reason behind that is actually the GPU is super parallel, right? So when you write to a certain data, you want to make sure this is done atomically. You can also lock a share. Basically, this is locking the sharing. This is what it looks like. So you have let's use the same example: load, address, increment, and then store back to this address. This is where you want to lock, right? So you have thread 1 coming in, you finish the load, you finish the increment, you finish the store. right before the increment, you lock the data. Right after you unlock it. This way, when thread 2 comes in and want to access the thread 1's data, let's say you want to do a load right here, you are blocked, basically, essentially blocked from loading that data. You have to wait until thread 1 unlock it. This is when the actual load happens. So this is load address, and you are not loading, you are waiting until you can actually load it. Waiting for the lock. All right. Any questions about mutual exclusion? Okay, so if there's no questions, if you've seen the PDF, I actually updated it. So I essentially skipped 2 slides because I realized you need some like hardware background for that particular 2 slides. You need to know the memory hierarchy. So if you have not taken system skill, you will get lost based on the 2 slides that I deleted. Right now, I'm going to talk about the in-class exercise originally designed for this week. Then I realized I need to talk about pthread, which means I will talk about it next week. Pthread is a library in C language where you can use parallel threads to generate parallel program. Your task is I'm going to give a starter code to have a share linked list. Your task is to properly lock the linked list. So I'm gonna put a starter code up on Canvas sometime this weekend. There's no rush to finish it. My goal is to make sure you know how to put in the lock and how to actually unlock them properly, so that if you need to in the future, if you need to deal with parallel program, you kind of know where to lock and unlock things. Basically, I will create 2 threads that perform list insertion and deletion because you share this linked list. There can be rest condition, right? So let's say this is my linked list. And let's say I want to insert this into the middle. What you need to do here is you get rid of this link, this point to here, this now point to here, right? What can happen is, what if the second thread want to access this linked list when I'm just at this point? I delete the tail that points to the next item, but I haven't finished done doing anything with the insertion. The second thread would see this shorter list without the rest of the list, right? So you need to lock this. When you need to do insertion and deletion, you need to find the exact line to lock your code. So if you know pthread, you can start now. If you don't, then I'm gonna give you the starter code and you basically put in the lock and unlock. My starter code will lock the entire program and unlock the entire program, which is not efficient at all. It becomes a single thread machine. Single threaded program. Your task is to change where to lock and unlock things. Any questions about this? But basically, this will start next week. I want you to practice running things in parallel beyond Rust, because Rust, while it's useful and powerful, when you start with someone else's code, there's a lot of time they use pthread because it's old, to be honest. It's been there for a while. It's pretty efficient, and if you know what you're doing, it's pretty fast. Okay, so Now that you talk about the shared memory model, the reason why I ask if any of you try running things in a cloud computing or not is because when you run parallel program, sometimes it's in a cluster. What is a cluster? A cluster is a bunch of computer tied up into this bigger network, right? Each machine has its own CPU and its own local memory, which means that if you need to access data on another machine, right? Basically, you have machine 1, machine 2, you have the CPU, and you have the memory. This is where your data is being stored, right? If you somehow need to access your friend's memory because that's where your data is, this particular type of access is called non-uniform memory access. The reason why we call it non-uniform memory access because these particular access will take longer than accessing your own memory because you need to go through the Ethernet. Basically, you need to go through the network. And running complex program in the cloud is relatively similar to this setup, right? This setup. So there will be chances that you need to deal with this non-uniform memory access, where each time you go to the memory, each time you access your array, graph, or any data structure that are big enough, some of the access can take longer. The reason behind that is if it's a memory on your machine, on your own machine, is just going through this on-chip network inside your chip, inside your processor that you buy, right? It's that small thing, the actual processor you plug onto the motherboard. Going to someone else's machine, you need to go to this off-chip interconnects. The interconnects can look something like this. Machine 1 connects to machine 2, connects to machine 3, which can connect to machine 4, right? And let's say going from here to here take one microsecond. So to get from machine 1, okay, I'm use a different color because now it looks confusing. To get from machine 1 to your memory, in machine 3, this is 2 microsecond plus time to access local data, which is just from the network interface to here, right? This typically is something like 100 nanosecond. To get from your CPU to your own local memory, this typically take about 100 nanosecond. So you see how this is actually about 10 to 20 times worse. If you need to go to the other machines to get your data, this can be a lot worse. Just to read something from your array, to read something from your vector or graph or something on someone else's memory, it can take more time. And that's a problem, right? The location of your data can impact performance. So there are multiple works that look into how to actually put data into your local processor. So these are basically research problem. If you're interested in any of these, let me know. The work I put here is one of my work when I was helping the first author out in 2013. We talk about how to map when you do malloc, how to map your data to as close as possible to your processor. How to link all the machine up can impact your performance as well, but it also burn a lot more energy. So you have to decide what you want to do. Load balancing, as I said earlier, can also impact performance. You don't want to schedule too many tasks to one machine, right? So these things are still kind of active area of research. If any of you are interested in this, it's actually kind of like dealing with parallel programming and operating system and distributed system and kind of like cloud environment in general. Feel free to check with me. Now that we're done with the shared memory model, which actually does take quite a bit of time, we will talk about the message passing model. Any question about the shared memory model? All right, so assume there's no question. Is there? So are you anyone here confused about what I'm talking about? Yeah, so basically it's just mutex for that model. You're correct. It's either mutex or atomic operation. You share the data. So the shared memory model, the name comes from the fact that you allow each thread to share the data. Each thread can look at the same point, like the same piece of address, the same piece of data, and they can modify it. Every thread has the right to modify that data, but someone else can put in the lock to prevent rest condition. So that's one of the like. So what your comment is a good summary to the shared memory model. To deal with the rest condition, use mutex or use atomic operation. Any other questions? All right, so if there's no more question, let's talk about the second model, the message passing model. Anyone heard about this model? Anyone heard about the thing called remote procedure call or RPC? Okay, good. So basically, if you never heard about this, basically it's the ability for you, when you're running on this computer, you can call the other computer's function. The other computer's function is a procedure call, right? The reason why you put the word remote is that procedure calls is not inside your computer. It's on the other computer. So here's the assumption. The big assumption here is every thread has its own private data. There's no sharing. There's no sharing over here. What you do if you need to share data, it means you are sending and receiving messages, right? You're just sending the data to the recipient, then the receiver would get your data, do something with it, returns the results back. Okay. So data exchange only happen through messages. That's why we name it message passing. You don't share data, you just share messages. If you want to tell someone this happened, send a message. Right? It's kind of like you are going on with your life. You never meet your friends. The only way for you and your friend to talk is sending messages. It's kind of like what we are right now, right? Under COVID and with the lockdown. We don't meet each other. The only way we can communicate is through instant message. So this is basically message passing. If you want to share something, send a message. If you want to receive shared data, wait for the message to arrive. Any question about this high level explanation? So here's what the message passing generally looks like. Let's say you have thread 1 and thread 2, right? And you're running program. Yay. Program 1. And let's say it's a part of the same program. It like combined into like one bigger task that each thread are running. T1 want to communicate to T2, you would first send the message. T2 once T2 receives the message, it would reply by saying, acknowledge, I got your message. And let's say that message say, run this function with this data. One thing T1 can do is send data. T2 will say, okay, acknowledge, I got your data, and then start running. What do T1 do? I'm gonna wait until I get a reply. With that, T2 can reply, and then T1 continue running. So these are the results. And T1 can say, acknowledge, I got your reply. So this is basically the basis behind message passing. Any question? So here's the actual implementation. When you have to implement the message passing, the beauty of this is you can, because you assume, right? Because you assume there's no sharing. When you have a computer, when you design a computer, the hardware right now, it doesn't have to support the fact that you share. What if T1 send multiple messages at once? So that's a great question. T1 can send a lot of messages too, as long as you know what you're doing. These are called, so what I draw here is called synchronous message passing, where you are waiting for the reply before you send next message. If you want to do it asynchronously by sending a lot of messages and waiting for the act, or maybe not, you need to make sure you have a way to handle what if your message is lost. Right? What if your message is lost? Are you resending the message? Are you going to queue that message and assume that, okay, I'll do that function on my own? So you can definitely send multiple messages as long as you know how to handle all the message you send, as well as the case where you don't get the acknowledge from the recipient, right? So these are more slightly more advanced topic where you can run into more bugs, but it improves performance quite a lot, right? So one thing that you will see once you use the GPU to run your program is the communication between the CPU and the GPU is similar to this. It's almost similar to message passing, actually. CPU will say, okay, send this data over. GPU will say, okay, I got your data. CPU will then say, launch this function. GPU will say, okay, I will run this function. Here is the result. Take it back. CPU will say, yeah, thank you. So this is one of the possible way to share data between two different machines. The beauty of this is when you have multiple type of machines, you have CPU from a Mac, like ARM processor, the one that I think is coming out soon. A CPU from Intel processor, and then an IoT device, and then you have a server that is running behind IBM Power 7, Power 8. You can use message passing because this is implemented inside the OS. The operating system will support this. It would know exactly how to deal with each of the data you're passing. The hardware hardware doesn't have to make sure you can support system-wide sharing, right? The message passing program, which is implemented in the system, will be handling this case. It allows you to connect a bunch of parallel machines that each of the machine might not look the same together, right? So supercomputer and cluster computing in many cases rely on message passing protocol, right? So instead of sharing through hardware support, which is the sharing in the first case, software implement sharing. The downside is this is going to be slower. They're not as efficient because the program has to handle communication. Any questions about this? All right. So if there's no question about this message passing model, we were gonna start talking about the last type of parallel programming paradigm. This is called data parallel model. And here are the main assumption. Basically, the main assumption is you have a lot of data. You have a lot of data. The operations now are done by performing the same function on every single piece of that data. For example, let's say you use NumPy. How many of you used NumPy before? Okay, so if you use NumPy before, a vector add is exactly running in this data parallel model, right? You want to do an add on every single element. It's one single instruction: add, right? How common is so let me ask you the next question. How common does this assumption hold on for programs that you are using these days? It's actually pretty common. Uh, in a lot of cases, you are applying the same function to other elements, right? Map, for example. Whenever you do a map, you apply the same function to all the elements in my collection, right? So here's a recap on why am I here? My bad. I skipped to the wrong slides. Assumption, numpy vector add. The second assumption that you have to apply is the data type has to be a sequence. You need to be able to get all the elements. Otherwise, if you have no way to get the sequence of elements, then you're screwed. Accessing the elements, you need to be able to access them through some operation. Basically, there has to be some certain function that you can write to get each element. And here's the operations. If you want to do a map, we went through this already. Operation is apply onto a collection. This can be done in parallel super easily. You can do additional optimization. For example, right? If you have back-to-back map, you have a back to back map, which is I'm gonna map uh, array A. I apply function f into array B, and then I apply function f prime into array C. Back-to-back map, it means that I can basically apply A directly into C into using a different function G, which consists of F and F prime, right? It's just kind of the same thing. So you can reorganize code to fuse the map together. You can prefetch data elements. So if you look at Intel assembly, there are certain instructions that allows you to get the data ahead of time. Take that data so that you can process it whenever you need the data, because you know exactly what elements are needed. Some of the operations in data parallel model are parallel for each. Right? For each item, the loop body becomes your function. So you map, basically, again, it's a map function. You map the loop body to each element. To communicate, you use gather operation and scatter operation. Gather operation, basically, I'm going to collect all the data that I want to apply before I apply the map. Scatter means that once I finish my operation, I'm going to scatter it back to the source that needs the data. So the way gather work is you typically have the index vector, and the list inside the vector contains the index to the elements that you need to gather. So let's say this is your array. And it starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. This is my index vector that contain 8 to 10. If my index vector is 8 to 10, here's what the gather operation would do. It would create an array with 4 elements, the same size as the index vector. It would check the first element. What's my index? 2. So you go to the second element, you put the result here. Go to the next element, 8. So you go to the index number 8, put the data there. 2 again, so you go to index 2, you put 2 there. 10, you go there and put 10 here. So let's say I change my array. I change my array into something like this. A, B, C, D, E, F, G, H, I, J, and K. If my index vector is the same, what is the result of my gather operation? Can someone tell me what's the result of my gather operation if my index vector is 2, 8, 2, 10? So that's a helper. So that's the index that I put in below the array. So if I have the index vector 2, 8, 2, 10, what is the result after I gather? C, I, C, K. Yes. Why is that the case? You go use the index, go to the array, you get that element, put it in the resulting array. My next question, can I do this scatter in parallel? Can I gather all the values in parallel? The answer is actually yes, because I'm not modifying anything in the original array. The only thing I do is I go search for that element. I'm going to put it back in the resulting array, right? There's no sharing here. There's no data sharing. Each element that I'm writing here is not shared yet. Not shared yet. The resulting vector is basically our element specify the index vector. That this can be done in parallel, and this can be implemented in the hardware as well. So these are instructions that you can use in the Intel processor that allow you to do this scatter, right? I'll skip the example because I already talked about the gather operation earlier using the example. Any questions before we talk about how do we get more performance? Okay, thank you for saying no so that I can move on. So basically, let's talk about traditional multi-threading. Right? As I said, each thread is assigned to run on a CPU. Each thread is running on a single node machine in parallel. It's shared memory that synchronizes data across threads using locks. Right? It also applies to NUMA machine where you have a cluster of machine. You can have the thread running across multiple machines where data is synchronized through messaging through the remote procedure call. So to get performance, this is kind of like a tidbit. Likely won't be important for your assignment right now, but might be a little bit more important for your project if you care about about the performance. Let's say we have a nice parallel program, and obviously the first thing we talked about last week, it should be work efficient. It should be work efficient. You don't want to do too much extra work to make sure you prepare your data in a way that you can run things in parallel. Parallelism should be decent. Something like log n is good enough, right? If you divide work and depth, if you get something in the order of like log n, that's good. Two big questions that you have and you should answer is how does this actually translate to performance and what else can we do to get more throughput, right? So first of all, you need to be able to measure how fast you can program things like flops, like instruction throughput. How many of you seen the word flops before? FLOP. Yes, no? No, the word flops. It actually common metric that okay. So that's a real life flop, right? The real life flop means something goes wrong and you flop it. So the flop is related to floating point operation per second. How many floating point operation you can do per second? It used a lot to measure GPU performance. The reason behind that is graphic operations care about floating point operation, and you want to be able to measure things like how many floating points you can do. In the CPU, when you talk about the Intel CPU, you might care about instruction throughput, instruction per second, how many assembly lines that you can finish in 1 second. You can know the upper limit by looking at number of cores, and we're not going to go too much beyond this because it's going to be repeated and repeated again. But at the end of the day, you can measure instruction throughput. You can also measure wall clock time, right? Wall clock time means that you measure your performance by looking at your actual clock, measure how long it takes. When you finish, you record how long it takes. It might be 1 millisecond, 10 milliseconds, 3 seconds. Those are execution time or wall clock time. So things that kill performance, which somehow broke the animation, Things like memory instruction. When you have load or store, you need to access memory. This takes about 10 times longer. This especially is true when you need to share big data structure. The CPU is actually designed to hide this long latency, and we cover this in ComArc. If you enroll in that class, we'll cover this in detail on how the hardware is being designed to kind of deal with this problem. But still be aware that if you're reading a lot of data, if you're loading a lot of data, that can lower your performance. If you're writing to a lot of things, if you're writing to a lot of shared memory, it means you need to apply so many locks that can also kill performance. Code branch, if else, can reduce the possible optimization that the compiler can do for you. That includes parallel. So the compiler, one thing they can do is to try to make things parallel for you. When you have a lot of code branch, this can happen. We will not cover this in this class because it's on the compiler topic. So this was from the last semester OPL, so we did have some time toward the end because we haven't really covered what we covered today in that class. So I ended up talking about the compiler a little bit and what they do and what's the compiler role in terms of programming language and performance. The hardware also suffer from branch prediction. So these, whenever you have branches that can lower performance, branch are if else or for loop. If it's easy to predict things like for loop, it's not too bad. But if it's if else that is hard to predict where you go, if it's going to the if or the else part, that can kill performance. Data synchronization and barrier. I hope by this time it's clear. Every time you lock something, that lower your performance because only one thread can run. And this get complicated as these can make your data cache out of date. What is data cache? If you take system skill, you know that in the CPU there's this small memory that is really fast. These data inside the small memory can become out of date. So that make your program slower. So share structure that are read only. What about this? Anyone want to take a guess about if I have a share structure that is declared as read only? Is it okay to have them? Is it okay to have a lot of these? All right, I assume all of you are kind of tired because it's been quite a while and from our last break, an hour and 10 minutes. So let me answer this. If you are sharing, but it's read only, this is exactly the same as read sharing in Rust. And this is okay for performance because you already guarantee no one modifies the data. So that can be done in parallel. Let's take a quick break before I resume and comes back and talk about something not supposed to cover in this class, but I really want to kind of talk about it on, okay, let's say we have parallel program. What else can the hardware do, which also include the GPU to make your program faster now that you know the three programming model, the shared memory model, the message passing, and the data parallel model. So let's do a quick break. We'll meet at 12:50. 12:50? Is that okay? 10 minutes break? Okay, let's do a 10 minutes break. I'm almost done with my monologue. We're almost done with all the lectures. After we are done with the lecture, I'm basically switching over to Discord, and then I'll have basically a long Q&A session about your projects. If you want to discuss anything, I'll be on Discord after this last, how many slides? Last 6 slides. All right, so let's meet again at 12:50. And yeah, and I'm gonna cover the rest of the lecture. All right. So I got a question whether this will be on the exam or not. So basically anything from this point on, anything from this slide on, are not going to go on the exam. These are some helpful things that I want you to hear about to some limited extent, where uh, uh, you can try to do something else on your program to hopefully make things faster. All right. So this topic is, I guess, not the primary material of this class. It is more like these are related stuff now that we talk about multi-threading, multitasking, parallel programming. So let's talk about hardware multi-threading, because what we can do is, instead of doing multi-threading in software or DOS, you can do that in the hardware. And this is actually done inside the Intel CPU and multiple CPUs that you have and you bought for your laptop, desktops, right? So these threads run different processes, and they are being designed to help the case where you have a lot of data load. Things like, I need to load a tons of elements in my array, things like for I equals 0, right? I is less than n, I plus plus, a of I, so let's say it's equal b of I plus c of I, right? These kind of code can take quite some time depending on how big is your cache, right? And when you have multi-threading, it allows the code like this to switch in and out of the processor, and the switching would happen a lot quicker. And so the benefit here is, if you have only one CPU to run things, you can run a different program. You can run a totally different program on the same CPU, which means that you can do what we call simultaneous multi-threading or Intel hyper-threading. Basically, if you look at Intel hyper-threading technology, it's this. Whenever you have a data load, and that data load take a few nanoseconds long, what Intel processor would do, it would switch to a new task. While you're waiting for that data, the other tasks are going to run. Then when you got the data back, the CPU would switch back to the old task. So that's what simultaneous multi-threading is. The key trade-off here is basically you require hardware support. So if you're designing the hardware, you need more complex logic, which means you need to have more transistor. At this point, because this class is not about designing the hardware, you don't have to care about this. But be mindful that this can go on. So let's say you have a CPU with Intel hyper-threading, you can enable this on your BIOS, and you might realize that your program, when you run together, might be a little bit faster. The reason why I said a little bit faster is kind of depends on how you run things, right? Sometimes you might get a few percent faster, sometimes maybe like around 5 to 10%, which is a little bit more significant. Another thing that the GPU uses a technique called fine-grained multi-threading, which is simultaneous multi-threading on steroid. Every time you do something, you have a new thread to put in the GPU. So that means you're going to have a lot more throughput. Don't worry about the text here. Basically, in the GPU, you group similar instruction, add, multiply into the same unit. Sometimes in NVIDIA terminology, you might have heard about it when you read articles or you're trying to understand how the GPU works so that you can run deep learning on the GPU. or you can modify the TensorFlow program on your own using C code and run it on a GPU. These terminologies called warp in NVIDIA and wavefront in AMD. They are exactly the same thing. It's a collection of threads. The threads that we talk about, right? The thread that we talk about. If you write it in a data parallel manner, the third programming paradigm that we talk about today, if you write in the third paradigm, which is data parallel program, they are likely to be runnable on a GPU. For example, vector add is really GPU friendly. So you can actually do that on a GPU. It will be done in basically almost instantly because the GPU can do those vector add for thousands and thousands of them in one cycle. How long is one cycle? Around 1 to 2 nanoseconds. That's why certain tasks will be a lot faster on the GPU. It performs fine-grained multi-threading on each watt to get even more performance. You need to assume data parallel program, right? So anything that I said earlier that kills multi-thread performance applies here. If you want to use the GPU, my key message is go back to the set of slides say things that kill performance. Every one of those would lower the performance of your program if you want to run on the GPU. Sometimes you might run your code on the GPU and you realize it's actually slower than running on a CPU. That can happen. You really need to slowly tune your program, optimize your program, and hopefully you squeeze out the performance by following the data parallel program paradigm. Any questions before we basically end the lecture and switch over to Discord? So that's it for today lecture part. The next part will be a long Q&A session, which I allocate about an hour for. Everyone here is welcome to join on Discord. The reason why I don't have in-class exercise for this week is if you have any concern, questions, anything you want to discuss about your project, this is the time. It would give you roughly good enough weeks, which I think 3 weeks, to cover the material that you need for your project and to make sure that your project is not too hard to finish. Right? So if you have any question about this, please join me over to Discord. I'm going to switch to my desktop. And then, so basically give me about a few minutes, like 2 to 3 minutes. I'm going to set it up on my desktop. And then we'll meet there. All right. So let me stop the recording. So that's it for the lecture part of this class.